Okay, before we talk about the next section, which is simplifying radical expressions, it is really beneficial to memorize all of your squares up to 20. So that's what I would recommend that you do. Here's the packet. Okay, then another good one to know is 25 squared. And if you know all of these, well, 20 squared is 4, like 400, 2 squared is 4. So like 30 squared is 900. 40 squared would be 1600. Do you see that? So you just take the number here and add 100 to it. So those are easy to do also. And then if you did like 300 squared, it would be 90,000, because you'd have 4 zeros. So you're doubling, when you're squaring, you're doubling the number of zeros you have. Okay. Right, so simplifying radical expressions. Okay, a radicand, that's the part underneath down here, right? Is in its simplest form if there are no perfect square factors, so there are no perfect square factors. Okay. There are no fractions. And there are no radicals in any denominators. And I suppose I should, there are no fractions under the radical. Okay, you can have fractions, you just can't have fractions under the radical. And you can't have radicals in your denominator. All right, so for any non-negative numbers a and b, okay, the square root of a b is equal to the square root of a times the square root of b. Okay, so basically, let's say I have 4 and 9, okay? The square root of 4 times 9 is the same thing as the square root of 4 times the square root of 9. And we can prove this. Square root of 36 is 6. 6 is the same as 2 times 3. Okay, so this is kind of your proof that this is true. Now, if I have numbers that are not perfect squares, let's say I have 3 and 7, well, if I get the square root of 21, it's the same thing as the square root of 3 times the square root of 7. Not that I can do anything with that, but it still holds true. If I figured out the decimal values of these, they would equal each other. We'll be using this fact to simplify radicals, all right? So if we have, let's say, square root of 80, okay? That's unattractive 80 right there. So square root of 80, right? There are two methods for me to do this. I can look at 80, and if I know that 80 is 16 times 5, that's the same thing as the square root of 16 times the square root of 5, which is 4 times the square root of 5. But let's just say hypothetically you don't know that 16 times 5 is 80. The second method we can use is factor trees. 80 is 2 times 40, and 40 is 2 times 20, and 20 is 2 times 10, and 10 is 2 times 5. Okay, that's completely factored. Then what I do, every time I have a pair that matches, I take one of them. Another matching pair, one of them. And whatever is left over, this 5, nothing matches that. Whatever is left over stays under the radical. And then you multiply whatever you took out and whatever's left over back together. So 2 times 2, 4, and then that 5 was left over. If there was, like, say, a 3 also left over or something, then there would be 5 times 3 or something. You know what I mean? Okay, we're going to try another one. Do the square root of 54. And I'm just going to kind of skip over here since I took up too much space. And if you know that 54 is 6 times 9, then that's the square root of, I'm going to change the order. Square root of 9 times the square root of 6, so that's 3 times the square root of 6. But if you didn't know that, 54 is 2 times 27, and 27 is 3 times 9, and 9 is 3 times 3. And I have this matching pair of 3's that can come out, and I have this 2 and this 3 left over, so they have to remain inside, and that gives me 3 times the square root of 6. Same answer. The last one that we're going to do like this right now is 180. Anybody know the perfect square inside 180? Me either. Now I know there's a 4. I know this will divide by 4, which would give me 45, right? And then 45 has a 9 in it. So there I found 2 perfect squares. So I can take the square root of each and do the leftover 5 stays underneath. But if I didn't think of that, I would have done my factor tree, and I would have seen that I have a pair of 2's, I have a pair of 3's, and I have a 5 left over. And so I'd have pulled out one of the 2's, one of the 3's, and left that 5 alone and gotten the same exact answer. Okay, multiplying square roots. Well, if I have the square root of 2 times the square root of 14, neither of these has a perfect square in it. But I can multiply them together and I get the square root of 28, which has a 4 in it. So I multiply them together to get a number that I can then take a perfect square out of. And again, if you didn't see that 28 was 4 times 7, you might see that it was 2 times, well, 14, and that 14 was 2 times 7. And then find your pair of 2's. We could try the square root of 5 times the square root of 10. Anybody know a perfect square that lives inside 50? If we start naming perfect squares, we've got 1, 4, 9, 25, or 16, sorry, 16, 25, 25. So I can take the square root of the 25 and the 2 gets left behind. That goes to there. And if you didn't see it, there's your pair of 5's. This one I imagine most people also don't know. 48 is 16 times 3. I know most of you did not memorize your 16s, which is okay. If I factored this, I would get my 2 pairs of 2's, which would give me this 4, right? And then that 3 left over. Okay. All right, now we have simplifying a square root with variables. All right, this is a little bit more intense. Okay. And we're going to ignore this 2 because I'm going to need that space. Okay. First of all, I need to look at each part of this individually. I look at the number and then I look at each of the variables individually. So starting with the 90. 90 is 2 times 45, which is 5 times 9, and 9 is 3 times 3. Okay. So I can take this pair of 3's, I can take one of those out. So it gives me a 3. And I'm not going to write it down yet, but I'm going to signify that the 2 and the 5 are going to get left behind. Okay. Then I have this x to the 3rd. Now how you deal with your variables is you take your exponent and you divide it by 2. And that leaves me 1 with a remainder of 1, right? 2 goes into 3 one time and with a remainder of 1. That means I can bring 1x out and 1x gets left behind. here I have a 4 on the y, so I do 4 divided by 2, and that's just 2, so that means I can bring 2 y's out. And none are left behind because I have no remainders. And then z to the 5th, I have 5 divided by 2, that's 2 with a remainder of 1. So I can bring out 2 z's and 1 gets left behind. So these are the things that are left behind. These are my remainders, my leftovers. So 2 times 5 is 10, and then I have an x and a z. Okay, so we have this 56x y to the 10th z to the 5th, and I want to take the square root of that. So first I need to look at my 56. That's 2 times 28, which is 2 times 14, which is 2 times 7. So I have this one set of 2's that I can pull out. Okay, so I'll pull that 2 out, and then this 2 and this 7 are getting left behind. I have 1x. So I can't take any out because I can't divide that by 2 even and get anything, right? So I'm leaving an x behind. I have 10 y's, so I divide that by 2, and that means I can bring out 5. I have no remainders, so no y's get left behind. And then I have 5 z's, divide that by 2, and you get 2 with a remainder of 1. So I can bring 2 z's out, and 1 gets left behind. So this is all everything that's left behind, right? Right here. So that's 2 times 7 is 14, and then x, z. Now we have the quotient property. There should be a y there, of square roots. So we have, for any real numbers a and b, a is greater than or equal to 0. So a can be 0. That's all right. But b has to be greater than 0. That's because we can't have any zeros in the denominator. And the reason we're saying it has to be greater than 0 is we can't have any negatives under our square roots, right? So if I take the square root of a over b, that's the same thing as the square root of a over the square root of b. And so if we use a real world example, we take the square root of 16 over the square root of 9, that's going to give us 4/3. And just to double verify that I am telling you the truth, if I take 4/3 and I square it, that's 16/9. Because it's 4/3 times 4/3, right? Which would give me that. So we can see that this is in fact true. Alright, so we need to rationalize the denominator. What does this mean? Rationalizing the denominator means no square roots in the denominator. That's what that term means. Okay, so what we do is, let's say we have the square root of 35 over 15. Now if you remember on that very slide a few pages back, we said you can't have any fractions under a radical. We also said you can't have any radicals in the denominator. Okay, so what you do to get rid of a square root, you square it. So whatever this is, you multiply the top and the bottom of the fraction by the same thing. In this case, we multiply by 1, so you know, anything divided by itself is 1, so we didn't change anything, but we get rid of the radical. So our denominator then simply becomes 15. And then our numerator is the square root of 525. Which is divisible by 25. So I get 5 times the square root of 21 over 15. And this 5 and 15 will reduce. So I have the square root of 21 over 3. Now I could have reduced at the very beginning. Do you see how here I could have reduced? If I had done that, so I would have had the square root of 7 over the square root of 3. So I would have multiplied by the square root of 3 over the square root of 3. Same process. It's just a matter of if you see that you can reduce or not. But if you don't see it, you'll still get to the same answer. Let's try another one. Try do you want to reduce first? We'll reduce first. Both 6y and 12 divide by 6, leave me y over 2. So that's the square root of y over the square root of 2. So I multiply by the square root of 2 over the square root of 2 so that the square roots cancel. And I can't take anything out of this 2y, so I'm done. And notice I'm not reducing, here I didn't reduce the 21 and the 3, and here I'm not reducing this 2 and this 2, because you can't reduce something under the radical with something not. They have to be both under the radical for you to reduce. Want to see one more? Okay, now we have conjugates. Okay, a conjugate, if I have A plus B and A minus B, these are conjugates. Okay. So we'll just ignore this one. If I have an expression like this, 5 plus the square root of 2, I want to multiply by the conjugate because I'm going to have to FOIL this. And when you FOIL conjugates, you get middle terms that cancel out. These two right here cancel out. Our middle term is going to have a square root in it, so my square roots are going to cancel out. That's why I need to multiply by conjugates. So I'm going to multiply by 5 minus the square root of 2 over 5 minus the square root of 2. Okay. So I'll FOIL this. So I do 5 times 5, so that's 25. And then I have minus 5 times the square root of 2 plus 5 times the square root of 2, and then minus 2, because the square root of 2 times the square root of 2 is just 2. That's my denominator. For my numerator, I'm going to distribute 3. So I get 15 minus 3 times the square root of 2. Now these cancel. So I have 15 minus 3 times the square root of 2 over 25 minus 2 is 23. Now if, in order to reduce this at all 3 of these terms, or these 3 numbers, would have to divide by the exact same number. So the 15, the 3, and the 23 would all have to be divisible by the same thing, which they're not. So this won't reduce. All right, let's try 7. Oh, let's try it in a color you can see. 7 over 3 minus the square root of 7. Okay. So I'm going to multiply by 3 plus the square root of 7. Okay. I'm going to distribute my 7 in the numerator to get 21 plus 7 times the square root of 7. And then I'm going to FOIL my denominator. So I do 3 times 3, which is 9, plus 3 times the square root of 7, minus 3 times the square root of 7, minus 7. I have these that will cancel, and that's over 2. And then 21, 7, and 2 don't divide by anything the same, so I'm done. Now just as, let's just say as an example, let's say I had something like that. 6, 3, and 3 all divide by 3, right? So this would actually reduce because I'd divide each of these by 3. And this would reduce to 2 plus the square root of 3 over 1, but we don't put over 1. So all 3 numbers would have to divide by the same in order to be able to reduce.